Okay, cool. Hi. This is great. I think I can fill the room with my voice. I love that. So I'm Randy Shoup. I'm going to talk about managing data and microservices, or managing data at scale with microservices and events. What's the way to say this? This was once upon a time a workshop that I gave that was an entire day. So it's a little bit aggressive to see if I can get through all the ways of doing shared data and joins and transactions in microservices. Oh, and by the way, talk about event duplication and event ordering and all that. But let's give it a try. So I guess I would say I'm hopeful that most of these concepts are at least familiar at some high level, and that what I'm going to talk about is some techniques in practice, how we do things at large scale. I didn't put a slide up about my background, but I used to work at Google and eBay, Stitch Fix, so a bunch of places that have actually done this stuff. Cool. But to start with, microservices, right? Lots of people are talking about it, but actually, lots of people are using it as well. So, and lots of places you've heard of it. So eBay, depending on how you count, is on its now 5th complete rewrite of its infrastructure. So it started famously as a Perl application that the founder wrote in a 3-day weekend in 1995. So he sat down in a 3-day holiday weekend over Labor Day in the United States and typed away. I always want to say typed away on his laptop, but I think it wasn't a laptop in 95. It was like a 486 tower probably under his desk that had like, I'm sure, I don't know, 1 meg of memory, some crazy thing. Anyway, so that was a thing that he just played around with to discover what he could do with this new thing called the web. That was the first version that ultimately became eBay. The second generation was a C++ application, an ISAPI actually thing, which at its worst was 3.4 million lines of code in a single DLL. So yeah, who thinks they have a monolith? Right, I understand that. So the next iteration was a rewrite in Java. To be honest, not because Java was better than C++, but because anything was better than 3.4 million lines of code. Java, you couldn't call that Java thing microservices, but it was absolutely mini applications, right? So the selling part of the site was one jar, actually ER file, that represented that application. There's another application for the buying part, another application for the search part, et cetera, times about 220 different individual applications that made up all of eBay. And now it's fair to characterize eBay as a polyglot set of microservices. Twitter has gone through a similar evolution. So it started as a monolithic Rails application, which of course they codenamed the monorail. The next iteration was a rewrite of the front end, mostly in JavaScript, a rewrite of the back end, mostly in services. They were early adopters of Scala at Twitter, so a lot of them were written in Scala. And then now it's fair to characterize Twitter as a polyglot set of microservices. Amazon has gone through a similar evolution. So it started as a monolith where the front end was Perl and Mason and the back end was C++. You can actually still see evidence of this monolithic application in some of the URLs. So if you go to old URLs that would have existed in the 90s, you might see Obidos, O-B-I-D-O-S in the URL. That was the code name of the original Amazon monolithic application. And Amazon, of course, is a river. Obidos is a city in Brazil on the Amazon, so that's why they called it that. The next iteration, which basically took them 2000 to 2005 to build, was microservices, mostly written in Java and Scala. And again, now it's fair to characterize Amazon as a polyglot set of microservices. Does anybody see a pattern here? Yeah, there are two though. The first is nobody starts with microservices. I think that's correct, by the way. But past a certain scale, which, let's be honest, not everybody is going to be eBay scale, Twitter scale, Amazon scale. But if you are, you have most places that I can think of have co-evolved to something that we now call microservices. Does it make sense? Yeah. All right, so this is the evolution. Again, not every company needs to be as massive to need microservices. But if you are that big, you definitely need them. So, I'm going to talk the rest of the time about how to deal with services at scale, but I do want to use a caution from Mark Fowler, which is, if you don't need this, don't use it. Don't use it. So I love Mark Fowler's, he's so wonderful. So, first law of distributed object design is don't distribute your objects. So my point here is, if you do not need Twitter scale, eBay scale, Google scale, Amazon scale, Netflix scale, then great. Don't hear me tell you that you should be in microservices, but if you are, I'm going to tell you how to get some of the things that you liked out of your small monolithic database with your small monolithic application. Does it make sense? All right, cool. 3 sections of this talk. The first is how we might migrate from a monolithic database, in particular, to a microservice approach. Next, I want to talk about, now that we're in microservices, how do we get those things that we loved about the monolithic database, like shared data, like joins, and like transactions. And then finally, I want to explore some of, and we're going to use events to do that. Finally, I want to explore some of the challenges that we will find when we enter the event-driven world. So things like event duplication and event ordering. Okay, cool. Great. So first, let's talk about migrating to microservices. But I guess I should pause and define what I mean by microservice. So the microservice is not like the number of lines of code. It's not how long it takes me to write the microservice. It is the scope of the interface. The scope of the interface, right? So it's a single purpose. It's got a simple, well-defined interface. And the idea here is that it's modular and independent. So if I write a payment microservice, I can use it to pay for lots of things. But the key thing that we have learned now in the 2000s and 2010s that we did not know, I'll say the I part of we, did not know in the 1990s when we first made an attempt at service-oriented architecture, was that last thing, isolated persistence. Many of the failures of service-oriented architecture in the 90s and early 2000s were failures because people built a bunch of services, but then they shared databases underneath. Why would that be bad? That would be bad because if I can read and write your data behind your back, what kind of guarantees can you make in your service? Absolutely none. Does it make sense? If I can read and write your data behind your back, the ability that you have to maintain variance, to maintain any kind of business logic in your service is essentially zero. So therefore, a thing that we have now learned is that in order for microservices to be effective, they need to basically have their own databases, at least their own logical databases. Is that making sense? Is this familiar? Okay, cool. That's going to be a source of problems, which we're going to then solve in the second section. Okay, but now let's imagine we, at Stitch Fix, where I used to work as of several weeks ago, let's imagine we have a monolithic database and we have a bunch of different services and applications that are using data out of that shared database, and let's try to migrate our way toward breaking that monolithic database up. So the problem is that we have this monolithic shared database. Why is that a problem? If this thing goes down, everything about the company goes down, as sadly has happened many, many times. It's also a single point of failure. It's a single performance bottleneck. It's a single point of contention for all of our development teams, right? So everybody is all in each other's business, to coin a term, all modifying the same schema. So that's a problem to be solved. And these are just some examples of some of the applications and services that we were running at Stitch Fix. We actually had 70, 80, some odd different applications and services, but there would be too many boxes and lines if I actually drew the actual diagram. Okay, so our solution is we want to decouple applications and services from this shared database. That's what we're trying to do here. So we're going to go through this step by step. The steps are going to seem simple, but they actually are complicated and necessary. So let's imagine, again, just to make it a little bit simpler, let's imagine we just had 3 tables in our database and we have 2 applications. So let's imagine we have an application that does styling, whatever that means, I can tell you later, and then we might have an application that is about storing things in our warehouse, because Stitch Fix is a clothing retailer. Okay, so step 1 is we're going to create a service. Let's imagine it's a client service, so this is a service about our clients at Stitch Fix, and that client service is using this table that's about clients. So the second step, which is the hardest step, is let's simply point the applications that used to use that table directly to the service. Now, I want to be super clear and underline that just this moving of these lines, that's the hardest part. Does it make sense what I'm saying? Decoupling, untangling, de-octopusizing, whatever, all that spaghetti, that's the hard part, but there is no way forward unless you have done that hard work. Does it make sense? So you can't move forward unless and until you've gotten to this point where the applications are not using this particular table directly, they are instead using the service. Okay? So we have made it to this second step, great, and now we have the ability to move that small table out into its own database that is, sort of local to the service. Does it conceptually make sense? Again, I want to underline this is actually hard work. and for that particular thing at Stitch Fix, I think it's actually still ongoing, so it's actually takes a long time to even do one of those extractions. But it's hard, but that's what you have to do. Okay, so now we have moved the client data into its own private database associated with the service, and now we can do that with the next table, and the next table, and the next table, right?
Can I take questions? Or
do you mind if we do it afterward?
Sure.
Yeah, just because I have a little bit of an aggressive, I have an aggressive schedule, but I will be here the whole, until Monday, so happy to talk more later. Cool. Great, hopefully we'll have a little bit of time to do that. Yeah, so now we just do that same thing for items, okay? So again, we have made the item service, we have stopped the applications talking directly to the items table, and then we have extracted that items table into a private database associated with that service. And then we do the same thing for SKUs, whatever that means. Does it conceptually make sense? Yeah, so I will say this, that I've done these kinds of extractions many times, and while what I just showed you seems like overly simple and maybe unsatisfyingly so, there is no way, I've yet to see a way forward that doesn't involve each of those 3 steps in that order. Does that make sense? All right, cool. So, and then the other thing to underline is, again, the service boundaries surround both the application part of the service and also the data part of the service. Does it make sense? So these are the service boundaries. They include, obviously, both, whatever you write your application logic in, Visual Basic maybe versus the, from the Keynote, or Con, with one of those, forget. I don't even remember. Mark? Contextualson. Yeah, if you write it in Contextualson in the 2040s, then go with that. Cool. Anyway, these are the service boundaries. Thanks, Mark. All right. Cool. So we're in microservices. We're all done. We can go home, right? No. Now the challenges really begin, because now we have a distributed system. Uh-oh. Okay. So now we're going to talk about managing data, the challenges of managing data when we don't have one database, we actually have 10 or maybe 100. Yeah? Cool. So I'm going to start with talking about 2 architectural tools that we're going to use in our toolbox to solve the problems. One that I'll call systems of record, another one that I'll call events, and then we'll go through some of the common things that we want to have. Again, shared data, joins, and transactions. Okay? Cool. All right, so let's talk about those 2 architectural tools we would like to add to our toolbox. So the first of them is this concept of a system of record. Is this a familiar concept for most people? Wow, surprisingly few. Okay, well, I'll explain what I mean. A system of record is the place that owns a thing in your system. Yeah. So if you care about, I don't know, clients, or you care about items, or you care about payments, there should be one and only one, I'll call it service, in your overall system that is the system of record that actually owns that thing. Okay? So there's one place in this particular example that owns the customer. There are many other places in your system that probably use customer, right? Customer is pretty important, so there are probably lots of places that use it. Every other place in your infrastructure that uses customer is a read-only, non-authoritative cache. Every one of those words is important, and I'm going to pause and explain what I mean. Okay. What do I mean by read-only? I mean the only place that I should be able to update the customer should be through that customer service. Does it make sense? That's what's meant by the system of record. It's not, every other place is non-authoritative, meaning if I ask the styling service or the customer search service or the billing service, hey, what's the current customer address? They might be able to tell me, probably they shouldn't, but they might be able to tell me, and if they tell me, they are only telling me a non-authoritative answer. Yeah, they're telling me a cached answer, which might be out of date by a day, an hour, a second, or a microsecond. Does it make sense what I'm saying? So anybody who's familiar with the vagaries of DNS, like that's this. Yeah, this is DNS. Like everything we think we know in 2010s, like my dad and all of his cohorts in the 1960s, they did it all. Yeah, read-only, non-authoritative cache. Does it make sense? And everything that we know about cache and cache consistency, those issues are also here. Yeah? So things, how do we update those things? Those are real problems. Okay, so system of record. There's one system of record. Everything else that references that thing is a read-only, non-authoritative cache. All right, cool. The second architectural tool, let's call events. And a thing that a bit disappoints me, but I'm gonna, whatever, I'll push through it, is that we don't use events enough, I think, in our industry. So Wikipedia defines an event as a significant change in state. I like to think of it as a statement that something interesting occurred. So customer address changed, customer was added, item was purchased, payment was processed. Does it make sense? These are all events that we talk about. Cool. In the traditional three-tier system that probably most of us, learn to program building, we've got a presentation tier, we've got an application tier, we've got a persistence tier. But what I think we are missing is we are missing a fourth fundamental building block of systems, which is some first-order concept of a state change, which I'm going to call an event. Okay, so this is the thing I want to motivate you, like we should be using events a lot more. So I will talk about now events in the context of microservices, and then we're going to use events to solve the problems of sharing data, of joins, and of transactions. Okay, so what I would like to think in services is that events are a first-class part of our interface. So the obvious part of my service interface is the synchronous request-response part. So maybe it is REST and JSON, maybe it's gRPC and protobufs, maybe it's, I don't know, DCOM or something, I don't know. But whatever it is, that's an obvious part of my service interface. Does it make sense? The synchronous request-response part. Other things that are also logically part of my service interface include any events that my service produces, any events that my service consumes, and also, we're not going to talk much about this today, but also any bulk reads and writes that might also be happening into my service, right? So bulk extractions that we do out of my service into maybe analytical systems, or maybe bulk loads into my system from some third party, like those are all conceptually part of the interface of the service. Does that make sense what I'm saying? And when I say part of the interface, I mean it needs to be managed very carefully, it needs to be managed in a backward compatible way. It doesn't mean these all need to be the same interface. We don't need to use REST and JSON for all these, but we do need to think about it as service developers, as all first order concepts. So the way I like to think about it is the interface for a service is any mechanism that gets data into or out of it. Okay? And sometimes this might be synchronous request response, or sometimes that might be asynchronous in the form of events. Okay, now we've got our architectural tools. Now let's use those tools to talk about sharing data. Okay, so let's motivate the problem. So in my wonderful, warm, monolithic database world, it was really easy for me to use shared data. All I had to do was simply point at the table and I was all done. Yeah? But where does this shared data go when I've broken up my monolithic database into a whole bunch of individual services? So we have two options, actually three options. The first option is simply look it up in real time. Yeah, so in this example, let's imagine I have a fulfillment service that is going to ship packages to customers, and it needs to know the customer's address. So it could simply go and call the customer service in real time, hey, what is Randy's address? This is a totally legitimate solution, by the way. Sometimes this isn't good operationally, right? Sometimes the load would be too high on the customer service, or the latency is too long, the response time from the customer service is too slow, or I like to say decouple the availability, so I might want to be able to fulfill packages even if the customer service is down. So if any of those things is true, then let's do option 2, which I'd like to call an asynchronous event plus a local cache. So the idea here is that the customer service is still the system of record for customer data, right? When I update the customer address, for example, that happens in the customer service. The customer service will send an address updated event whenever a customer's address is updated. The fulfillment service will simply listen to those events, and it will cache locally the customer addresses. Does it make sense? So, and lots of service, lots of systems in our world work like this. Cool. This is a legit solution too, just like the first one. A third solution, which works really only when it's slow changing metadata, is thinking of distributing things via code. So at Stitch Fix, we were a clothing retailer. We had metadata like what are the sizes? What are sizes of clothing, right? So small, medium, large, extra large. Those things are rare changing, like it's rare to have an extra large, although we don't have to wait too long in the US for like that to be needed, sadly. The colors, actually, to be honest, the colors have actually changed over time, not because we got new colors, but because new colors became popular and needed to be first order ideas, right? We had pink, and then, oh, you can't say pink for men in the US, so it better be salmon, that type of idea. Fabrics, the list of fabrics. The US states, or maybe the countries in the EU, for example. That is slow changing. If there are any changes in the number of countries in the EU, we're going to have a lot of knowledge about that ahead of time. Well, just leave it at that. Ditto the US states. We have 50 US states today. I hope someday Puerto Rico might become a state and maybe we will care about them and send them aid. Yeah, if that actually happens, that's not going to change in a microsecond. So there's no reason for me to do a service lookup to say, what are the US states? Still 50? Cool. Anyway, so what we do for these types of slow changing metadata is we distribute it via code, and then we can version it can be in version control, etc. Right? But this is a solution that works for that class of problem. Make sense? Cool. All right. That's sharing data. Now let's talk about joins. So let's motivate the problem. In a monolithic database, it's very easy for me to join tables together. I just simply add another table to my from clause and I'm good, right? So I've had once upon a time I had select from A. Now I have select from A, inner join B on some join condition. Great. But now that I've split the data across microservices, I can't do it just by editing SQL anymore. So what do? Two options. The first option is just join it when you need it. So just join it in real time when you need it in the client application. So in this particular example, let's imagine we're going to build an order history page in Stitch Fix. So we want to look at all of a customer's orders, and we might also need some information about the customer herself, like we might need her name or I don't know, something we want to say about her. So we want to go to we could go to the customer service and get her information, yeah? And then we could separately go to the order service and get a list of the orders of hers. Does this make sense? Again, a totally legitimate solution. There is absolutely nothing wrong with this. This is every web page on the planet. This is every web page on the planet that doesn't come from one single call. Yeah? Cool. So there's nothing wrong with this. This is totally legit. Okay, but again, sometimes operationally we want to decouple availability, or the latencies would be too high, or the load would be too high. So now we want to do potentially something called in option 2, which I will call a service that materializes the view. Have people heard this term, materializing the view? I'm very intentionally using database terminology here because that's kind of what we're doing. So in this example, I used a slightly different example. So let's imagine we want to combine together items that we have in inventory, things that we have sold, and we want to combine with that customer feedback about those items. So each item we've sent out many times to many different customers, and we've gotten many different pieces of feedback about those items. Does it make sense? The problem? And I want to, for whatever reason, I want to show that or maybe use that for analytics. Okay, cool. So in this example, I'm going to create an item feedback service, which is going to materialize the join between items and order feedback. So it's going to listen to events from the item service, when new items are created, when new items are deleted, maybe if items are updated in some way that matters. And then it's also going to separately listen to events from the order feedback service, like whenever we get a feedback about one customer's order, we can join that. And then this service is going to maintain in some form, it could be in memory, it could be on disk, it could be in a database, but it's going to maintain in some form a denormalization or a join of those two things. Does that make sense? So again, for those people who raised their hand or nodded about materialized views, that's exactly what this is. But managed for you typically by database, right? So if you're not familiar with materialized views, probably that means you're not using an enterprise class database, i.e. one that you pay for. By the way, we use Postgres, so that's fine, nothing wrong with that. But yeah, like Oracle, SQL Server, like a bunch of the enterprise class for pay databases have this concept of materializing views. Make sense? So again, you choose between these things whether you need, if you need a fancier technique, and you actually need to reify a join, then you can do it in its own service. All right, cool. Okie doke. And if that seemed unfamiliar, I want to convince you that there are lots of systems you already use that do that materializing a view technique. So, like I mentioned, these enterprise class database systems, have that as a first order feature. Almost every NoSQL system that you use, if you use Cassandra or React or Voldemort, almost all the time you're actually upfront doing that denormalization. People who use those systems are nodding. Any search engine that you use, if you use Elasticsearch, almost certainly you are joining together pieces of data from different parts of your infrastructure because people like to search on lots of different things. That's great. And anybody who has an analytical system, like Hadoop or something like that in your infrastructure, almost for sure that analytical system is a join of lots of different entities in your system. Does it make sense? So again, if this picture on the last slide looked unfamiliar, then I want to let you know that actually there are probably lots of things in your system that already do this. Cool. All right. The tour is going quickly. So that was joins. Now I want to talk about transactions. So here, let's motivate the problem. In a monolithic database, it makes transactions across multiple entities very easy. So I can simply express, whether in my programming language or in my SQL, I would like to begin a transaction, I would like to maybe do one or several inserts, I would like to do one or several updates, and then I will commit. Right? Familiar to everybody? This is so wonderful and so safe and so warm when you have one database. But when I have multiple databases, this becomes hard. I really like Pat Helen. Who's familiar with Pat Helen? He is also brilliant like Mark and also hilarious like Mark. What he said way back in 2007 when he wrote this excellent paper called Life After Distributed Transactions and App Estate's Opinion, he wrote this. He wrote, in general, application developers simply do not implement large-scale applications assuming distributed transactions. And then when he gave a talk after that, he said it a little bit more bluntly. He said, grown-ups don't use distributed transactions. We could spend a whole hour, maybe several, talking about why that's true, but very simply, a distributed transaction involves lots of different, we say resources in academia, like lots of different resources that are all involved in the transaction. If any of them is down, you're out of luck. If any of them is slow, you're in worse luck. Does it make sense? So just conceptually, that's why people tend not to use distributed transactions at scale. Who uses the cloud? Keep your hand up if your cloud vendor implements distributed transactions. You're wrong. Nobody. There are no distributed transactions in any cloud vendor that I'm aware of. Yeah, nothing in Azure, nothing in Google Cloud, nothing in Amazon. Why? Nobody does it at scale. Okay, silence, wow. Is this sad? Are people like, is this just, you're just hearing this? Cool, all right, cool. But yeah, so no distributed transactions. Again, conceptually, academically, yes, they do exist in the world. There are lots of great, two-phase commit, three-phase commit. There are lots of distributed communication, or rather coordination protocols, but in practice, people at scale don't do them because of the failure modes, because of the slowness, etc. All right, cool. Okay, well, I can't have a transaction, Randy. What can I have? Well, I will tell you what you can have. You can have a workflow, or you can have what we also like to call a saga. Who's heard this term? Wow, lots of you. Awesome. This is great. Wow, cool. The way that we think about this is, so conceptually in my transaction, I would like to update A and update B and update C atomically, right? Like that's what I would like to do. I would like to have it happen all, I would like to have it all happen or not at all, yeah, atomic. I would like to, obviously, atomic, consistent, isolated, and durable. Well, let's see, you can't have the atomic, you can't have the consistent, you can't have the isolated, probably you can have durable though. Okay, cool. But instead, we're going to re-implement this thing as a workflow. So conceptually, what we're going to do is we want to update A, B, and C all in one go. We can't do it all in one go, but we will have a situation where at the end of some process, which we'll talk about, we have done the A update, we have also done the B update, we have also done the C update. Immediately you are saying, yeah, Randy, but what happens when there's a failure? Great question. Whoops, great question. Thank you for asking. The way that we deal with a failure is that we produce events that go in the other way. Yeah? So, sorry, what I didn't say in more detail, I'll say a little bit more detail about this before I do the failure case. So the workflow is something like, I'm going to update A transactionally, because there's only one database about A. Yeah? Then that's going to produce an event, which then B will listen to. Yeah? Then B can do its part of the transaction. It will produce one or several events, and then C will be able to do its part of the transaction. Does that make a little bit more sense? So it's a workflow that starts with step A, it produces some event that lets us know that we have to do step B, which produces some event that lets us know we have to do step C. Okay, so if there is a failure in that path, then we do this. Then we roll back by applying what are called compensating operations in the other direction. Yeah? So if we need to undo this thing, we do an operation on C that says undo the work that we were trying to do, undo this workflow, that produces one or several events, that causes B to undo its work, and then that causes then A to undo its work. Does this conceptually make sense?
What's if A is already changed?
Could we do the questions at the end? Just because I want to be fair to other people in line about questions. Yeah, I mean, hopefully we'll have time to talk about it. Like there are ways of, there's both an orchestrated way to do this and a choreographic way to do this. If that matters, if people know what I'm talking about, they know what I'm talking about. If they don't worry about it. But yeah, I'm showing this in the choreographed way where it's, individual services are independent of each other and they produce events. There's another way of thinking about it with a transaction coordinator that makes sure that A and B and C have actually all happened or not at all. Another way, so people who have a computer science background or have been around computers for a while will have heard of a state machine. State machine? That's what this is. This is a state machine. And so when you think about a state machine, you think about intermediate states and you think about terminal states. Yeah? So another way of saying the idea of saga is I have two terminal states, which is we have completed the operation that I want to do, yeah? Or we have rolled back all the operations that I want to do. Does it make sense? So it's a state machine with a terminal state that's at the end. A and B and C are all happy, and there's another terminal state at the other side, which is nothing happened to C, nothing happened to B, nothing happened to A. Okay? Cool. If this seems unfamiliar, I want to suggest that any system that you use that has any kind of workflow is exactly like this. For example, who is familiar with payment processing? Everybody. Okay. I would love, let's imagine that I would like to pay Mark for his amazing keynote. Ideally, I would like to take my wallet out of my pocket and hand a credit card to something, and then atomically and magically, the money immediately is sucked out of my account and immediately ends up in Mark's wallet. Is that what happens?
No.
No, it super does not. When I have given this talk in New York, I like to point out that every building that was around me is built by the fact that the money that comes out of my account takes 3 days to get to Mark's account. Right?
One more.
Where people are laughing, like, why is that true? Also, the London City, by the way. The City of London. Like, all those buildings are built essentially on the idea that my money that goes from me to Mark takes a while to get there, and those people can do lots of speculation and lots of investment with that money in the interim. Does it make sense? Yeah. Payment processing. Again, it is not atomic, but it does actually happen and work in the real world. Yeah, it does actually happen. And there are terminal states. The terminal state is that Mark actually, the money is actually ultimately extracted from my account, ultimately goes to Mark. Or there's a terminal state where there was some failure along the way and Mark doesn't get the money, but I get the money back. Does it make sense? A thing you will also notice is we can observe intermediate states. So you could ask, what is the state of the payment from Randy to Mark? And for those 3 days, the answer is, it's pending. It's pending. That's legit. That is a legit answer. Yeah? Another example is expense approval. So anybody who's here and is, has their way paid for by your organization, if you go to a jazz club or something and you have to, submit that as an expense, that goes up the chain, like that's your boss and her boss and her boss, and there have to be all these approvals. Again, it's not atomic. The expense approval that you get is not atomic. It's a workflow. Does it make sense? Another thing, who traveled here? Who lives here? Here in Mallorca? Seriously? Awesome. You guys are wrong. So everybody else who does not live here exactly in Mallorca traveled here. It took you actual time to get here. So wherever you started, whether it was London or Vilnius or San Francisco or some other place, like you started in one place and you traveled for a while via planes and trains and automobiles typically, all the way and you got to here in Mallorca. If you asked, where is Randy? If you asked like 20 some odd hours ago, if you asked, where is Randy? I don't know, somewhere over the Atlantic.
En route.
En route. Where is Randy's travel? What is the state of Randy's travel? It's pending. It's processing. Does it make sense? So I tell you these not because these are terrible things, but because there are lots of things we reason about in our regular lives that are exactly this. Does it make sense? So if you can read, so again, taking a step higher, if you can think about that transaction that you wanted to have all at once as one of these workflows, and you just simply make clear when somebody asks, what's the state of this thing, you say, yeah, it's pending. That's a legit answer. And so if you think about, if you use those ideas, then you can think about these in a useful way. The last metaphor here I just can't ignore, which is who codes for a living? Okay, keep your hand up if when you hit return in your IDE that it is immediately and atomically deployed to production. Let the records show that no hands remain. Like, I'm a big fan of continuous delivery, but that violates the laws of physics, what I just said. Again, how could you possibly reason about a system where the code that's in production is like a different state than the code on your laptop? Dude, you do it all the time. Yeah? Your job, 8 hours, 10 hours, 12 hours a day maybe. Like, your job is doing that. Like, you're building new stuff on your laptop. Now we can say laptop because nobody has a 486 tower, I suspect, anymore. So you're building it on your laptop, and if you are, I really feel sad for you. If you're building your code on the laptop and then you deploy it, right? You put it into source control, you, I hope, run a lot of tests, then you ultimately deploy it, and then it goes to production. Does it make sense? And you can say, again, in the interim, what is the state of version, n+1 of the code? Oh, it's being deployed, or it's pending, or it's processing, or something like that. Does it make sense? Cool. All right. Enough of that. Oh, one last thing I want to say about workflows and sagas. Who has heard of serverless? That's a terrible name, but what it is, functions as a service. Functions as a service are excellent for event-driven processing, where it's mostly stateless, and that's exactly what we're talking about here. Does it make sense? So a good use of Amazon Lambdas or Google Cloud Functions or Azure Functions would be something like this. Does it make sense what I'm suggesting? Cool. Again, because it's initiated by an event, it's mostly stateless, right? And it produces some other event on the other side. That's exactly what, one of the many things that, Lambdas and functions as a service were implemented to do. All right, cool. Great. Now, in the remaining 12 minutes, I will tell you everything you need to know about event-driven systems. Yikes. Okay. Cool. Not everything you need to know, but some good things. Okay, so great. So now we have services. Randy, you taught us how to do data, do joins and transactions. We're all good, right? No, because we're using events, and events are hard. So let's talk a little bit on why they're hard. 2 reasons that I want to talk about. There are more, but 2 main ones. I want to talk about event duplication, and I want to talk about event ordering. So the first event, the event duplication, the problem here is that the same event will be delivered more than once to your consumer. That is a fact. Get used to it. Okay, because there might be network issues, there might be redelivery, there's lots of reasons for that to happen. So your consumer, if you've received event 2 twice, you have to at least logically process that event only one time. Logically. Okay, there are several techniques. The first technique is some concept of exactly once delivery. We can separately talk theoretically about why that might be a challenging idea, but conceptually, some transports at least claim the idea that, okay, if there are multiple events that get delivered, they will only deliver that event, that get produced, they will only deliver that event once to your consumer. Does it make sense conceptually? How does that actually work? There's no magic, it's simply buffering up the events, noticing what it's already sent, and if it gets the same event twice, it only delivers it once. Does that make sense? All right, that is one way of dealing with this problem. The other way of dealing with this problem is not making it a problem. Having a consumer that is idempotent, right? Having a consumer that, if I get the same event twice, I only logically apply its work one time. Yeah? So a way to do that, among several that I will discuss, is something called an idempotency key, if people have heard this. So the sender, the producer of the event, will mark the event with some unique key, and that allows the consumer to deduplicate it. Yeah? Cool. All right, so in this example, it's marked with this key BBB, and so you can see that the state doesn't change even though it's received the same event twice. Yeah? Another way is that the processing that we do is just inherently idempotent. This is rare, but if you do something like, if your operation is something like set a value to 0, like you could just set the value to 0 many times and it has the same effect, right? An upsert, like an update or an insert, like in one statement, that's another example of this, right? Anybody who's programmed in a database often has this thing where like, I want to insert a new record, but like maybe it's already there. So you do a thing where it's like, if it's not there, insert it, otherwise update it. Is this sounding familiar? Right, the concept is it's called an upsert. Postgres has that, by the way. But yeah. Cool, okay, that's the option 2, is that your processing is inherently idempotent. That's rare, but sometimes happens. Option 3 is a fancier set of techniques that the generalization is something called conflict-free replicated data types. Who's heard of these things, CRDTs? Yeah. The idea here is that we're trying to achieve agreement between two things without any explicit coordination. It typically involves custom data structures, some composable processing steps. There are lots of implementations. There's actually a lot of active research, even in PhDs, going on right now. And how do you know that? It's because whenever somebody gives a talk on CRDTs, it starts with, what is a CRDT? So if you ever, by the way, like a tip that I will give you, attending conferences, if there's ever a talk that is about like, what is X? Do not use X. Because it's not good. Yeah? Good. Enough laughter that you got my point. All right, cool. So if my talk was, what is a microservice? Like, do not use microservices. But we're beyond that now. All right, cool. Some common techniques. I'm not going to talk, I mean, there's a whole hours of conversation we could have about CRDTs. Two techniques that they often use are a technique that's kind of like an idempotency key, which is remembering what they've already processed. That's one technique that's commonly used. And the other technique that is not obvious is if something is deleted, remember that it was deleted. And that's called a tombstone. Just want to like, if you ever hear these terms, I want to just sort of familiarize with them. All right, cool. What I will say though is building something like a CRDT seems super simple. Please do not do it from first principles. Like, these things are hard, so take advantage of tens of years of research, please, to do that. All right, cool. All right, now I want to talk finally about event ordering. So we talked about duplication. There's lots of different ways of handling the fact that we might receive the same event twice. Now I want to talk about what happens if I receive events out of order. Yeah? All right, cool. Let's motivate the problem. Events are going to arrive out of order. Get used to it. Why is that true, Randy? Well, network issues, right? So, you know, we might have some network delay, processing time, like it might be difficult to, you know, might take a long time to process something. Events might be re-delivered, right? Because the message bus thinks there was a failure, so it doesn't know that it already delivered event 1, so it might deliver them out of order, that kind of thing. Anyway, so for whatever reason, we're going to have to deal with the fact that events might be delivered out of order. And so again, what we need conceptually is we want the consumer to correctly work, even if there are events that are delivered out of order. Like that's the problem statement. All right, cool. So several techniques. The first set of techniques of all are basically imposing an order. Having some place in the system where we take things that are out of order and we reorder them in the correct way. So a place we could do that is in the message bus, yeah? So we might receive events out of order. So here we've received event 2 before event 1, and the transport might be buffering everything up, again, like the last time. And so the transport might reorder it from, I say transport, message bus, that's kind of what I mean. It might reorder it correctly and then pass it on to the consumer in order. Okay, like that's a legit solution. How does this work? The transport's just buffering. There's no magic. Right, it's just buffering. So that's, you know, potentially an issue if it takes a long time to get that event. All right, so message bus is queuing or buffering messages, waits for those gaps to get filled magically, and the bus sends to the consumer in order. Okay, cool. Option 2 is that we're going to receive things potentially out of order and reorder them in the consumer. Yeah, so again, the transport delivers things out of order, but the consumer, again, buffers and reorders. Who's heard of TCP? That's this. Again, by the way, every problem in computer science already solved in the 60s. All right, cool. Great. Except for the great new problems that academics are solving, so sorry. All right, cool. Great. Okay, so one class is somebody reorders. Another class is order independence. Yeah, that we don't care about the order for some value of don't care. Okay, so the first option here is that semantically we don't care. So again, this is rough for me to find good examples, but like let's imagine the consumer just simply wanted to count the number of events it saw, then it doesn't really care about order. Does it make sense? Like this is a super rare case, but you could imagine something very simple that was this. Okay, so the option one is that, look, my semantics order doesn't matter to my semantics. All right, cool. Option two, which is pretty common actually, is what I like to call notification and readback. So the event itself is a notification that something changed, but the event doesn't actually carry the state, or if the state is carried, it's ignored. And what happens is the consumer goes back and reads from the original service and says, hey, what's the current state? Yeah? And because it's done that, now it sees the current state correctly. Does it make sense what I'm saying conceptually? So the event is simply a notification. The consumer knows that it has to go back and read from the system of record, hey, what's the current state of, I don't know, the customer or this order or this payment? And then it learns the current state and then all good. This is how eBay implemented its messaging system, by the way. Conceptually make sense? Cool. And then the final option, which we should not be able to do a build stuff without talking about event sourcing, is event sourcing. So a way to think about it is we store all the events in a log, and then later we can, if we need to, we can reorder them. Yeah? So the idea here is that the transport delivers things out of order, the consumer actually logs them in the order that it hears them, that's totally fine. And then, when we are asked, which may be never, but when we're asked, we can, if necessary, reorder the events. Does it make sense? Or maybe we could, in the background, we could be reordering things. Like there's lots of ways of doing it. But the conceptual idea is that we just store all the events in a log, and then we process or maybe interpret them in order later. Wow, okay, cool. So, we talked about migrating to microservices. We talked about once we're in microservices, how do we get those wonderful things like shared data and joins and transactions. And then, for a bonus, we talked about some of the challenges that we have to deal with around event-driven systems. So, muchas gracias. Okay, so we do actually have a few minutes for questions. Hi.
Well, that's very specific for that we were talking about it. The migration from a monolithic application to microservices.
Yeah.
In your example, you had tables that you one after the other move outside of the system.
That's right.
Services. Mostly we have, that's what I experienced. Mostly there's not one table that doesn't relate to others. So usually I have basically a big ball of mud inside my database.
Yeah.
And this is.
Yeah, no, that's a great
question. It's
the statement. Yeah, so just to say that, totally agreed, and we have that same thing, which is why that step of like repointing things, why that's the hard step, is it's typically lots of tables are interrelated to each other. So in the nice case, you have a core, you have like a central table that's the entity, and you have a sort of constellation of child tables. That's not what you're talking about.
That's spider.
Yeah. That's the easy part is you move a set of tables that are around the entity all together. Like you can imagine, the main entity and then attributes about it, something like that. Like that's typical in entity relationship model or entity relationship model. Sorry. Yeah. Anyway, yes, that's the simple case. The normal case is that there's lots of spaghetti. And my point is, you cannot avoid cutting that cord in some way. And that doesn't mean that cutting the cord is easy. I mean, I know you know this, but like cutting the cord doesn't make it easy. But you just cannot move forward until you have cut that cord. Yeah.
Just made it look very simple.
That's why I stopped and said this is the hard part.
Yeah.
It's because it is the hard part. But yes, as you correctly underlined, it's the really hard part. Yeah.
Yeah, I was wondering, you will going back, I was wondering if you actually have to use logs so you can locally
Okay, so we are in the
rolling back,
yeah.
But then you explained that it's something like stateless. But there was nothing.
Yeah.
Would you like a log A until you reach C, and then C is accessible, then you can.
Would you need to lock anything? I can't think of examples where you, well, let's say it this way. We would like to try to get to a situation where we define away the need for that lock, and so we have to do that, obviously we have to do that at a bit of a higher level. So again, let me try to start at the higher level and hopefully end up with some useful place. So at a high level, again, we have to model the thing that we're trying to achieve as a workflow of separate steps. Yeah? And so, and again, we can, I mean, just to restate the obvious, because we have modeled this thing as a workflow of separate steps that are each atomic but not together atomic, it means you can't observe interim states. You can observe interim states in the forward motion through the state machine, and you can also observe interim states in the backward motion through the state machine. Yeah? So if the semantics of your system are such that you can't observe interim states, yeah, we should talk about that. And in fact, we should probably, I mean, I'm not putting you on the spot, you don't have to do this now, but like, if there's a specific example, maybe we can work through it. Typically those situations where people say, yeah, but I can't separate A and B, it's because they're actually logically the same service, if that makes sense. Like that's actually logically one operation, if it conceptually can't be separated, if that makes sense. You know, in my experience, I've rarely found a situation where I could not break up like several steps into several steps, if that makes sense. Yeah. Again, it's hard to have, it's a legit question. I will say that it's hard to have this conversation in general. Like, if we take a specific example, then I think we could together work through, oh yeah, well A and B, that's clearly separated. Oh, but B needs to be together with C or something like that. Does that make sense? Cool. Yes, please.
Yeah, in that system, you point out there, you like work with explicit rollbacks.
Yeah.
One thing that we also found that sometimes you don't need to do a rollback if you make your system in such a way that whatever is left, if it's in a pending state, it doesn't actually matter.
Yes.
And you kind of avoid these like rollbacks,
Yeah.
which can also fail and can also go out of order.
Yeah. As with all interesting things, this could be its own talk. And yeah, so techniques you can use are explicitly rolling it back, either in this choreographed way or with a coordinator, with an orchestrator, right? That's another legit approach here. But another common technique, I'm going to get to yours, but another common technique is to have a batch, like cleanup every so often. Yeah, that goes through and goes, all the payments that have not already been processed after, I'm making this up, 24 hours, like wipe them clean. Or, to your point, even better, define the semantics of your system in such a way that if you don't complete it, it's invisible. Yeah? eBay did that. So the common technique for a master detail relationship of, let's imagine that I have a user in eBay and she has bought items. So the common technique is like first you create the user and then you create the item that refers to the user. eBay did that in the reverse. So they would first create the detail and then create the master. Why? For your thing. Because if you create the detail and you fail in creating the master, you can't find the detail. Yeah? Yeah. So again, excellent point. What I showed is the hard case, where you have to actually clean it up. But yeah, to your point, I guess the generic of all engineering problems is how can I define this problem away? Yes. How can I make this problem not a problem? And only if I cannot define it away, okay, fine, I'll solve it. Yeah, cool. I'm going to be around for the rest of the conference, so I hope we'll have more fun discussions. Thanks a lot.